In this video, we're going to be looking at ways to estimate areas under a curve. And one of the ways that we're going to do that is using something called the rectangular approximation method. Now, finding area under a curve, this is kind of what we're looking at today is kind of a precursor to the real power of an integral. And so this is kind of a preview of what you can see and what you should expect from looking at integrals in future sections and throughout this course. So in this example, we say we have a train that moves along a track at a constant rate of 75 miles per hour. So it's moving at a constant rate. The speed is not fluctuating. So we want to know what is the total distance traveled by the train from 6 a.m. to 9 a.m. So we're going from 6 a.m. to 9 a.m. So if you recall, right, all the way back to like algebra, when we talked about finding the distance, we know that distance is equal to our rate times the time that we are traveling. So if I wanted to calculate this, so this curve here is representing our velocity function with respect to time. So the constant rate, that's our velocity. So our train is traveling a constant rate of 75 miles per hour. So this here is 75. And it's happening from 6 a.m. to 9 a.m. Okay, so to find the total distance, right, our distance is just going to be, man, I cannot write right now. Our distance is going to equal the rate, which is 75 miles per hour, times the time that they travel. So if they're traveling from 6 a.m. to 9 a.m., this is a total of 3 hours. And so that is 75 times 3, which is 225 miles. Right, so intuitively, that kind of makes sense, right? That kind of makes sense. So we're traveling 75 miles per hour for 3 hours, so that gives us 225 miles. Now, if we take a little closer look at what we have in this situation, we have our velocity function and then the time that we are traveling. If we were to kind of construct what we have here, right? So we have a rectangle, basically. And really what we just found, this total distance, could also be representative of this area in here. It could be representative of the area within this rectangle here, right? Because if we think about this in the fact that this measure here is 3 hours, this height here is 75, we know that the area of a rectangle is base times height, and so that would also give us 225 miles. So really what we just found is the area under this velocity curve, which represented our total distance. Remember, distance is part of position, right? Part of position. So we found something out about the position of our of the train when we were looking at the velocity with respect to time. So to go from velocity to position, we would have to do an antiderivative. And so this is kind of like I was saying, a precursor to the power of integrals. And this is nice, right? We have a nice rectangular curve or function here, so it's easy to find the area. But what happens if we have something like this? What do we do in a situation where we have something that is not rectangular? I don't know how to find the area of this. This is a curve, right? So how do we estimate or calculate the total distance traveled in a situation like this, where the velocity is not constant? So how would we estimate this area? So one suggestion that I would make is we could just try and make it close to a shape that we know, right? So I could probably estimate the area if I used a rectangle, right? What if I used a rectangle here? So what if I made this shape here a rectangle? Could I estimate the area under the curve with this rectangle here? Well, it's close, right? It might be close, but it's not going to be exact. And we could make it closer, perhaps, by using smaller rectangles, right? So like what if I used rectangle here, and then another rectangle here, and then another rectangle here, and another rectangle here, and I just used a bunch of rectangles, and I summed all of their areas. and use that as an estimate. So that's another way that we can do this, and that's going to bring us to our idea of this rectangular approximation. So in the second example, we want to estimate the distance traveled when the velocity varies using these different measurement estimation or approximation methods. So these are rectangular approximation methods. So this one here is called left endpoint rectangular approximation method. This is the midpoint approximation method, and this is the right endpoint rectangular approximation method. So we have, in this situation, a particle that starts at x equals 0 and moves along the x-axis with a velocity function v of t equals t squared for time t greater than 0. Where is the particle at t equals 3? So basically it's asking us how far has this traveled? What's the distance that it's traveled in 3 seconds? Now remember, the position is the antiderivative of the velocity, right? I take the derivative of position to get the velocity. So the antiderivative would give me my position. So basically what we're trying to find is we're trying to calculate this area under the curve, and that area under the curve represents the total distance that we traveled. And because we would have traveled from a position of 0, then that's going to be our position, our final position. So for this, we have our curve here. That's our velocity function. And what we're trying to do is we're trying to estimate this area in blue here. And we're going to do it in 3 different approximation methods: left endpoint, midpoint, and right endpoint. So what we're going to do is we're actually going to cut this, this region into 6 subintervals that are of equal width to try and calculate. So let's start with left endpoint. So left endpoint. So basically what the left endpoint approximation means is when you are drawing your curve, you're going to line your rectangles up so that the left endpoint of the rectangle is touching the curve. So these points here are going to represent the height of your curve. So your height is being calculated by the left endpoint of this interval. And then the left endpoint there would be that. So how would I find the area, right? So we know that the area for a rectangle is equal to the base times the height. And so we need to calculate the base and height for each of these rectangles and then use that to try and find the area. Okay, so what is the base? What is the measure of the base? Well, we know that we divided this into 6 subintervals. So basically you can find the base by taking the starting point, so we're going from 0 to 3, and dividing it by the number of subintervals. So we can find that by saying b minus a divided by n, where n represents the number of subintervals, and we're doing this on the interval from a to b. So this is 3 minus 0 divided by 6. So that's 3 over 6, which is 1/2. So the width is going to be 1/2. So all of these points are half a unit. So this is like 1, 2, this here is 0.5, this here is 1.5, and then this here is 2.5, right? So those are their values. Now how do we find the height? So the height is just going to be equal to the value of our function, right? You can see the height is represented by so the height of this rectangle is the same as the value of my curve at that left endpoint. So this curve here is t squared. So if I wanted to calculate the value here, it's just going to be v of 2.5. And then if I wanted to calculate the height here, it's going to be v of 2. And then the height here of this rectangle is v of 1.5, 1.5, and 0, respectively. So the height is just going to be the velocity function evaluated at the left endpoint. So if I wanted to, I could kind of take a look at all of these rectangles that I get and then calculate their areas and use that as that sum to approximate the total area under the curve. Now, because we're using left endpoints, and this function is increasing on this interval, you can see that it's going to be an underestimate, right? Because all of this space in here is not getting accounted for. And that's true anytime you have a function that is increasing and you're using left endpoints, you will have an underestimate of the area. Okay, so we can approximate the area by saying, so let's look at this first rectangle here. So this first rectangle kind of doesn't even really look like it exists, but its base is 1/2. Its height in this case is f of, or v of 0, which is going to be 0. And then for this rectangle, it's, again, its base is 1/2. Its height is v of 0.5. So if I plug in 0.5, that's 0.5 squared. So it's half squared. Well, that's really small. You can't read that. Sorry. 1/2 squared. So that's this one here. The area of this rectangle is going to be, again, 1/2 times. We're looking at the left endpoint. So it's 1 squared. Plus the area of this rectangle is going to be, again, 1/2 times. In this case, it's 1.5 squared, or 3/2 squared. This one here is going to be, again, the base is 1/2 times the height there is 2 squared. And then let me move this stuff over just a tiny bit. Try and make some space for it. And then this last one is going to be 1/2, which is our base, times this left endpoint here, which is 5/2 squared. And then you can just plug this into your calculator to come up with your approximation. Now, one thing that you might notice is all of these terms have a 1/2 in it, right? Have a 1/2 in it. And that's because we divided it into 6 equal subintervals, right? Because all of our rectangles have the same base. So if we really wanted to, we could have factored out the 1/2 here, and it would have just been 0 squared plus 1/2 squared plus 1 squared plus 3/2 squared plus 2 squared plus 5/2 squared, right? And you could have calculated it this way. And you're always going to have 6 subintervals, or 6 numbers, right, for the number of subintervals. So 1, 2, 3, 4, 5, 6, and that represents the heights. These are the heights of your rectangles. So if you go and you plug all this stuff into your calculator, you would get that the area is approximated by 6.875 square units. Which means we've traveled 6.875 units from where we started. So that would be the distance that it traveled. And so this is using left endpoint approximation. The next one is midpoint approximation. So this one is sometimes a little bit more challenging because you have to locate the midpoint of your subintervals. So it's not always as nice of numbers, but it's another approximation method. Now, this one is a little bit more accurate, I would say, because you can see that while it overestimates a little bit here, it underestimates by a similar amount there. And that kind of happens throughout this whole, the whole part of the curve. So we might get a little bit more accurate estimation with midpoint approximation. So again, we have this divided into 6 subintervals. So now this here is 1/2, 3/2, 5/2. So again, we have area is equal to base times height. So the base in this, again, is 1/2. Again, is 1/2. This time, our height, in this case, our height is equal to the velocity evaluated at the midpoint, right? So we're trying to find the midpoint of each subinterval, and we're evaluating our velocity at those values. So what are those measures? Okay, so you can see like our midpoint is here. It's going to be halfway in between that there. So midpoint there, midpoint there. So you can see that all of our midpoints are now representing the heights of our rectangles in this. So what are our midpoints? So halfway between 1/2 and 0 is going to be 1/4. So basically we're going to be adding 1/4 to all of these. So this is going to be, 3/4. And all of these should be half a unit apart as well. So if I add a half to this, that's going to be 7/4. So because we're adding 4/4, we should be adding 2/4. My mistake, 5/4 here. The next one here is 7/4 in the midpoint. And then here would be 9/4. And then the last one is 11/4. So those are our midpoints that we're going to be evaluating. I can spell, this should say height. Sorry about that. This is our height. So to calculate the area. The area is equal to, again, all of our rectangles have a base of 1/2. So I can really just pull that base measure out. So it's 1/2 times our velocity evaluated at each of the midpoints. So it's going to be 1/4 squared plus 3/4 squared plus 5/4 squared plus 7/4 squared plus 9/4 squared plus 11/4 squared. Okay, and then go ahead and plug that into your calculator, and you will get that the area is roughly, it's estimated by, if you just did all of this in your calculator, it would be 1/2 times 17.875, which when you divide by 2 is about 8.9375 square units. So we have moved roughly about 9 units in this case, in that case. And this is the estimation that we get from midpoint approximation. So if you compare that to the left endpoint, you can see that it's higher, right? And you can see that should be pretty obvious because all of these are underestimating. While in this one, a little bit of this piece is above and then a little bit of piece is below. So you would think that this is probably going to be a higher value. For the last one, we're doing right rectangular approximation. So if you would, I would like you to try and do this one on your own. So remember, to calculate the height of the rectangle, what you're using is the right endpoint, the right endpoints here. So these are our right endpoints that we're using to approximate the height. So you're going to be looking at the value of our velocity function at these endpoints. So again, remember that these are all split into halves, and these are our intervals here. Okay, so go ahead and pause the video and try and see what you can do for estimating the area with this one. All right, so now that you've given this a try, we should see, you should have something like this, right? So each endpoint here is, so this endpoint that represents the height would be V of 1/2. That's going to give us the height of this rectangle here. V of 1 would give us the height of this rectangle. V of 3/2 gives us the height of this rectangle, and so on, right? All the way up to finding V of 3 to give us the height of this rectangle. So if you square, because the velocity function is V of t is t squared. So if you square all of those right endpoints, you should have this. The bases of all of our rectangles are 1/2. And if you calculate all of this, you should get an approximation of 11.375 square units. Now, in this situation, we can see that all of these pieces are going to be, this is going to be an overestimate of our area because, again, so our function is increasing. And in the case where you use a right endpoint on an increasing function, you end up with an over approximation because all of these pieces of the rectangle are hanging out above the curve here. And so this would be our approximation for, with a right rectangular approximation method. In this last example, we are given the function f of x equals cosine of x, and we want to let a be the area of the region that lies under the graph of f of x, where x is between 0 and pi over 2. So we're looking at, so if we have the graph of this curve here, we know that this is 1 here. We know that it hits the x-axis at pi over 2. So we're basically trying to find the area in here under the curve. Now, because it's not constant, we don't know how to find that actual area, so we're going to estimate the area using rectangles. And it says estimate the area using MRAM, so that's midpoint rectangular approximation, and 4 subintervals. So if you recall, the area for all of our rectangles is going to be equal to the base times the height. The base, its measure is, again, it's b minus a divided by n. So that's going to be pi over 2 minus 0, which is pi over 2, divided by n, which is 4, which is the same as multiplying by 1/4. So all of our rectangles are going to have a base of pi over 8. And then what is the height? Well, the height is basically just going to be the value of our function at the midpoint. So the height is going to equal f of the midpoints of each of our subintervals here. Okay. So we can cut this in half here. We know this is pi over 4. So here's pi over 4. Cut it in half again. We have pi over 8. And then if I add pi over 8 to pi over 4, that's going to give me 3 pi over 8. And so we want to make our rectangles here. So if we draw rectangles, we can kind of draw them like this. And now remember, they're intersecting at the midpoint here. So the height of the function, right, the height of our rectangle is going to be intersecting there at the midpoint. So let me just duplicate some of these. So this one here. So your intervals really should be equal, but clearly mine are not. So you'd have your 4 rectangles here. Wow, I did a pretty terrible job here. I probably can fix this and make this look a little bit better here. So I probably will do that. Let me do that here. Make this a little bit better. So that's a little bit better. But basically we're going to be at the midpoints. So all of these points are going to be the midpoints for the heights. So this one should be down here like this. And that's how we're going to be finding the heights of our rectangles is going to be from the midpoints of those subintervals. So really, if you drew this better, which I didn't, we should be looking at evaluating our function at the midpoints of all of these intervals. So what is halfway between 0 and pi over 8? Well, that's pi over 16. Halfway between pi over 8 and pi over 4 is going to be 3 pi over 16, right? Because remember, we're also adding, we're adding pi over 8 because that's the length of each subinterval. So this is going to then be 5 pi over 16, and then this last one is going to be 7 pi over 16. Okay. So if I wanted to calculate my areas here, so the area is going to be approximated by the base. Now all of these have the same base measurement of pi over 8. So it's pi over 8 times the function evaluated at the midpoint. So the function is cosine. So it's the cosine of, and then all of our midpoints. So it's going to be pi over 16 plus cosine of 3 pi over 16 plus cosine of 5 pi over 16 plus the cosine of 7 pi over 16. Sorry, this is a 7. And you would go ahead and throw that into your calculator, and you would get that the area under this curve is approximated as 1.006 square units. And remember, we want to keep our decimal points out to 3 at least. So that would be our estimated area under the curve.